Okay, welcome back. This is more integration in Calculus 2. In particular, the partial fraction decomposition method is what we're worried about. 8.5, partial fraction decomposition. We'll just call it PFD for short. And what is it all about? It's about making one fraction into two fractions. Okay, making one fraction into two. Right, so generally you can, recall if you have something like x minus 3 all over x, you can take that one fraction and make it into 2 by doing a butterfly. So you get x over x is 1 minus 3 over x. But unfortunately, if you have something like x minus 3 all over x minus 2 times x minus 5, let's make it even worse, right? You could still pull that off, but this case, we don't know how to turn that into two fractions. You can't butterfly that numerator. If you have like 3x there, you can't say it's 3 over x minus 2 plus x over x minus 5. That won't work. Okay? So you need a way to turn this thing into two different fractions, x minus 2, x minus 5, because the deal is integrating this thing is going to be hard, right? But integrating these things, whatever is in the numerator, these are easy because these are just natural logs. Okay? This is just a times the ln of x minus 2 is b times the ln of x minus 5. So if I have a way of converting this into this, that would be great. And at this point, believe it or not, you just don't have that, right? We spent a lot of time teaching you how to go in the other direction from finding a common denominator to make it in the one particular fraction, but not this direction. And please note again, this case is not the same as this case here. Okay, so this is kind of neither here nor there. So anyways, that's what the beginning of this section is dedicated to. It's just the process of going from one fraction to two fractions. And it's more complicated in general than the other version. A lot of things in math are like that. It's easy to take it apart, hard to put it back together. Right? A lot of things in real life are like that. It's easy to break an egg. It's hard to put the egg back together. So anyways, the partial fraction decomposition of the form some numerator function over some denominator function, and where these guys are themselves polynomials. So first off, if the degree of the numerator exceeds the degree of the denominator, you'll do long division. Even if it's equal to, do long division. So if the degree of the numerator function is greater than or even equal to the degree of our denominator polynomial, then do long division. Okay. It's only these other cases that we'll worry about the partial fractions. So otherwise, then do this part A. Otherwise, go to part B. So B, right? How does this work? So first, we just want to deal with setting it up. Okay. So the setup will kind of look like this. We'll have some sort of fraction, and then we'll create numerous fractions based off of the denominator. So I gave one fraction for this denominator, one fraction for this denominator. That's kind of the case. Okay. As far as denominators go, if you're dealing with a polynomial, there's only two kinds of factors possible in the denominator. Well, actually, the book will cut it up into 4, right? So the two possible factors are linear factors and then irreducible quadratic factors. Okay, so you could take any polynomial and break it down into things like x minus c times x minus c2 times x minus c3. But there might be the case of x squared plus bx plus c terms in there, because we wouldn't be able to factor unless we include the complex numbers. Okay, so the setup is based off the flavor of the polynomial, and the first in the denominator. And the first type we're going to look at are linear factors. And their form, you know, the equation of a line, there'll be mx plus b, right? So instead of mx plus b, let's say something like, I don't know, ax plus b. Okay. Some things that are linear factors may not look like linear factors. So examples of linear factors, x is a linear factor. 3 minus x is a linear factor. 2x plus 1 is a linear factor. Okay, so anything like that is a linear factor. So let's take a look. Let's look at some examples, right? So example, first one, I have 8x minus 1 all over x minus 2 times x plus 3. Okay, so for each factor in the denominator, you're going to create a fraction. That's just given. Okay? And then depending on the type of denominator, so here our denominators are both linear factors. The numerator will just be a constant in this case. And we'll label it A, B, C, D, E, F, G, etc. Okay, so A up here, B up here, that's it. That is really it. Some more examples just to convince you. Here's x plus 34 all over x squared minus 4x minus 12. In this case, you have to factor the denominator first, right? Because right now it looks like it's a quadratic factor, but in fact you can factor into two linear factors. So you'd have x minus 6 and then x plus 2. Okay? And sure enough, these are both linear. I don't really care about the numerator at this point. I just need one fraction for each factor. And then the numerator, if these are linear, I'm just putting A, B, C, etc. One more example, 4x squared minus 5x minus 15 all over x cubed minus 4x squared minus 5x. Again, I got to factor the denominator. This would be x times x squared minus 4x minus 5. So x times, I can factor this thing into x minus 5, x plus 1. And then I need one fraction for each factor. So 1, 2, 3 fractions. I need one fraction for the x, one fraction for the x minus 5, and one fraction for the x plus 1. Okay. Across the top, you go A, B, C. Okay. These are just the setups. We'll get to actually integrating here later. You're just going to have to bear with me as we go through these different forms. The second form are repeated linear factors. Okay, so if you have like x minus 5, x minus 5, x minus 5, in other words, x minus 5 cubed, that would be considered a repeated linear factor. Okay, okay. So you'll handle these a little bit different than before. Okay. So you have x minus 1 cubed, which is really x minus 1 times x minus 1. So you need 3 fractions here. One for each factor. And then in the denominator, it's a little bit different. You're going to put x minus 1, and then you work up to the power of the exponent. So then x minus 1 squared, and then finally x minus 1 to the third. Across the top, it's business as usual. You have A, B, C, and that's how it goes. So get one more example. 2x plus 3 in the numerator again. X squared times x minus 3 times x minus 2 squared, or maybe x minus 1 squared. Okay. So in the denominator, I need there are 2 factors of x, so I need 2 fractions, 1 factor of x minus 3, so 3 fractions, and then 2 more fractions for this repeated linear. Okay, so for the first repeated linear, the x, I go x and then x squared. And then I need a fraction for this non-repeated linear, which is just x minus 3. And then the last repeated linear, x minus 1, and then I need to go up to x minus 1 squared. Across the top, it's just business as usual, A, B, C, D, E. Okay, so we hope we don't see a big one like that, but it happens. Right? It happens. Right, so that's the repeated linear factor. As far as proving this stuff, there's no real rhyme or reason at this point. If you studied like number theory, which is like more of a junior level class for math majors, then you might actually investigate this phenomena. I don't think we investigated it when I took number theory, but you may get lucky. Of course, you always have access to the internet. You can go on there and figure it out on your own, right? Okay, so it has something to do with number theory. We don't explain it. I don't know how intuitive it really would be. Anyways, let's look at the next case. Irreducible quadratics. Okay, so in algebra, you can always break down any polynomial into linear factors like this, as well as quadratic factors, where the quadratics aren't necessarily factorable in the real numbers. You need complex numbers to factor a lot of these, right? So a major example would be something like x squared plus 1. So back in elementary algebra, they had taught you that this thing is prime. You can't really factor it, right? You can't say it's x plus or minus and then 1, because you're always going to have an outer and inner term to add together that's going to give you like 2x or minus 2x in the middle. So this thing is considered irreducible in the real numbers, and that's what we're calling an irreducible quadratic. It's something I can't break down unless I use imaginary numbers or something like that. So when you see those, you're going to do the following method. For example, here I have x squared plus x minus 6 all over x squared plus 1 times x minus 1. Right? So I break that. I'm going to need one fraction for this factor, which is irreducible. I just kind of showed you that. This does not equal that. It's not true. You can't factor it. And then I need one fraction for this factor. So for the irreducible quadratic, x squared plus 1, and then I need a factor for the fraction for the x minus 1 factor. And the numerator of an irreducible quadratic, what you're doing is putting a linear factor. So you're going to write ax plus b. Okay? For this linear factor, then you just put a constant up top. So it's like you just go 1 degree less for the numerators. Let's look at another example of that. Okay. I have x squared minus 1 all over x cubed plus x. Okay. So I need the factor of the denominator. You can always factor into even quadratics and linears. So if I factor out an x, I get x squared plus 1. And of course, this is an irreducible quadratic. So I'll need one factor for the x, or one fraction for the x factor, one fraction for the x squared plus 1 factor. And then this is linear, non-repeated, so up top put a. This is irreducible quadratic, so you go bx plus c. Okay, one more. Okay. I need to, again, factor the denominator. So if I factor out an x, I'll have x squared minus 4x minus 5. Whoops, I think I already did this example. I apologize. I already did this example. I'm sorry. Let me just make up one to make up for that. So 2x plus 1 all over x squared plus 4 times x minus 2 squared. Okay, so I need one fraction for the irreducible quadratic, and up top I have to put ax plus b, so x squared plus 4. And then plus, I'm going to need two fractions for this. It's a repeated linear. Okay, so x minus 2, and then plus x minus 2 squared. And up top of this one, I put c. Up top of this one, you put b. Okay. Okay. So the last kind is the repeated irreducible quadratic. And those repeats work the same way as the linear repeats. So you're just going to put a fraction for each factor of the repeat, and you'll increase the exponent all the way up to the number of repeats in the denominator. Okay, so let's take a look at two examples of those. We have 8x cubed plus 13x all over x squared plus 2 squared. So it's a repeated irreducible quadratic, so I need two fractions, the x squared plus 2 to the first, and then another one, x squared plus 2 to the second. Up top still, you need to put these linear expressions, so ax plus b, and then plus cx plus d. Okay, let's look at a really hard one. And if you can handle this one, I think you can handle any of them. Okay, so here is a repeated linear. I needed three fractions for that. Here is non-repeated linear, so an extra one. This is repeated irreducible quadratic, so two more, and then an irreducible quadratic for one more. So 1, 2, 3, 4, 5, 6, 7 fractions is what I need. So one for the x, one for the x squared, one for the x cubed, and then one for the 2x plus 7, one for an x squared plus 5, one for x squared plus 5 squared, and then a last one for the x squared plus 1. Across the top, A, B, C, D, and here I have now quadratics, so you need things like EX plus F, GX plus H, and then IX plus J. Okay, so that's as bad as they'll get. Now we want to worry about finding these actual constants, and then lastly we can worry about integrating it. Okay, so first off, finding these constants. There's two different methods. One always will work. The other method does not always work. Right? Both methods are important, though. There's actually methods in differential equations called equating coefficients in order to find solutions. So this method will carry over into other classes. So hopefully you don't blow it off. Okay, so I'm going to show you the hard method first. So maybe we should give this a new title. I've sort of forgotten where I am in my notes. I think 2. So part B was set up. Part C now actually solving for numerators. Okay, so method 1 is the equating coefficients method. And it always works. And not only that, later on there's techniques in differential equations when you're solving those things that you'll use this sort of method. Okay. All right, so anyhows, equating coefficients, note the following factoid from algebra. If you have ax to the 4th plus bx cubed plus c, and that equals 5x cubed plus 2, you could say the coefficients over here equal the coefficients over here. Okay? In other words, let me rewrite this as ax to the 4th plus bx cubed plus 0x squared plus 0x plus c. And on this side, I have 0x to the 4th plus 5x to the 3rd plus 0x squared plus 0x plus 2. I can figure out what a, b, and c are just by equating the coefficients. So the coefficient on x to the 4th has to equal the coefficient on x to the 4th over here. So that would be 0. The coefficient on x cubed here has to equal the coefficient on x cubed there. So b would equal 5. And likewise, And then I just see C, okay, C is 2. So that's the idea that we want to exploit in order to figure out these numerators in this first method type. So let's look at number 7. I'm given 5 all over x squared plus 3x minus 4, but we're going to factor it. So x plus 4 times x minus 1. And then we do our setup. Okay, so I'd have a fraction for x plus 4, and then a fraction for x minus 1. Across the top in the numerator, I'll have a and b. Okay, and now the method kind of ensues. So what I want to do first is to multiply to get rid of the denominators. And what that comes down to is multiplying the entire equation by this denominator here. Okay, and then everything gets multiplied by it. So this times this side, the x plus 4, x minus 1's cancel, and you're left with 5. This times this, the x plus 4's cancel, leaving you with a times x minus 1. Then this times this, the x minus 1's cancel, leaving you with b times x plus 4. Okay. Then I go ahead and distribute the a, so I'll have ax minus a plus bx plus 4b. Okay, the order of terms here, it's always going to go constant, like 5, and then big letter, capital letter, whatever that is, a, and then your variable. Okay, so the big letter always goes in between the constant and the variable, just in case you're wondering. Okay, now we're going to collect like terms together. So 5 is ax plus bx, and then minus a plus 4b. And then I'm kind of equating coefficients. It's not clear what the coefficients are until I kind of factor. So a plus b times x, I factor out an x. And then this term you think of as negative a plus 4b. So equating coefficients now. On this side, there is not really an x variable. So you just put like a placeholder there, 0x. Okay. And then you equate the coefficient of this x and this x. So a plus b must equal 0. And what you're ending up with is a system of equations. Right here, negative a plus 4b is equal to 5. And then you use whatever you want to use to solve the system. Okay? Usually I just do substitution, so a is negative b. So I can plug negative b in here. Negative b is b, plus 4b is 5. In other words, 5b is 5. In other words, b is 1. Okay? And then plug 1 in for b here. A is negative 1. And that does it. That tells us the partial fraction decomposition. In other words, 5 all over x plus 4 times x minus 1 is equal to negative 1 all over x plus 4 plus 1 all over x minus 1. Okay? Okay, so that's the hard method, but it always works. The shortcut method, which you'll definitely prefer, but won't always work, is the second method, too. And it starts after I multiplied through by the denominator. So the beginning is just like before. Okay, so I do my setup. Then I multiply through to get rid of the denominators. So I have 5 equals a times x minus 1 plus b times x plus 4. And then what you do is just clever substitutions in order to eliminate the big variables. Okay, so if you let x equals 1, you're going to eliminate the x, you're going to eliminate a, and you'll be left with an equation in terms of b. So look, you have 5 equals a times 1 minus 1 plus b times 1 plus 4. 1 minus 1 is 0, so 5 must equal 5b, and then b is equal to 1. If you let x equal -4, then you have 5 equals a times -4 minus 1, and then plus b times -4 plus 4. This time, -4 plus 4 is 0. B times 0 is 0. The b goes away, and you're left with an equation in terms of a. Divide both sides by -5, and a is -1. So you get the same answer either way. This method is almost doable in your head. Okay? We'll need both methods, unfortunately, for our class. Let's dive in here now and actually do some integration with the partial fraction decomposition. Okay, so section 3, actually now doing the integration. Okay, so let's start with number 9. They're telling us to integrate x squared plus 12x plus 12 all over x cubed minus 4x dx. Okay, so you'd still want to check to make sure the degree of the numerator is, in fact, actually less than the degree of the denominator. In this case, it is. The partial fractions won't work otherwise. Okay, so you'll get an answer that is not, you'll get an answer, but it won't work. Okay, okay. So anyways, this is something you do in partial fractions on. So let's do that. X squared minus plus 12x plus 12 all over this thing factored. You can factor out an x, you get x squared minus 4. So you'd end up with x times x minus 2 times x plus 2. Okay. So let's do our setup. It's a over x plus b all over x minus 2 plus c all over x plus 2. Okay. I'm going to do the long way this time. So I'm going to multiply everything by this denominator. It'd be x times x minus 2 times x plus 2. Okay, this denominator would be gone when I multiply that times that. So I have x squared plus 12x plus 12 equals this times this. The x's go, and I have a times x minus 2 times x plus 2. And this times this, the x minus 2's go, and I have plus bx times x plus 2. And then finally, this times this, the x plus 2's go, and I have c times x minus 2. Okay, so x squared plus 12x plus 12 equals x minus 2 times x plus 2 is x squared minus 4. So I'll end up with ax squared minus 4a plus, distributing this, you get bx squared plus 2bx, and then distributing this, plus cx squared minus 2cx. Okay. You want to collect like terms together and start equating coefficients. So I have an a b, and a c, x squares. You can factor the x squares out of all those, and you get a plus b plus c times x squared. Okay. And then the x terms, so I'll have plus 2b minus 2c x, after you factor out the x from this guy and this guy. And then finally, the constant term is just minus 4a. Okay, so now we can build a system of equations. A plus b plus c, it must be equal to 1. Okay, the coefficient on x squared here is equal to the coefficient on x squared here. So a plus b plus c must equal 1. And then the coefficient on this must equal the coefficient on that. So you have 2b minus 2c is 12. In other words, b minus c is 6. And then finally, minus 4a is equal to 12. In other words, a is equal to -3. Okay. Okay. So now we want to sort of do substitutions and all that jazz. Letting a equal -3 in this equation gives me with b plus c equaling 4. I can add this equation to this equation, and I get 2b equals 10. So I just did the addition rule for solving equations. So I'm using both substitution and addition rules. Divide both sides by 2. I get b is 5. So finally plug that into here. 5 plus c is 4. So c must be -1. And those will be our our numerators. Okay? So I can now rewrite my integral way back there as the integral of -3 over x plus 5 over x minus 2 plus -1 all over x plus 2. And that's dx. So none of these really require u-subs. You won't have any constants to worry about. So you could just straight up do logarithms. It's -3 ln absolute value of x plus 5 ln absolute value of x minus 2 minus 1 ln absolute value of x plus 2, and then plus your integration constant. And that's it. Okay. Let's do another one like that. So when you have irreducible quadratics, that's when you have to do the first method, the equating coefficients method. Let's look at 25, the integral from 1 to 2 of x plus 1 all over x times x squared plus 1 dx. So again, the numerator's degree is less than the denominator's degree, so I'm going to be doing a partial fractions. Here I have an irreducible quadratic. So first off, a all over x for the linear part, and then plus bx plus c for the irreducible quadratic. Right, I'll multiply through by x times x squared plus 1. You'll end up with x plus 1 equaling, well, a times x squared plus 1 plus x times bx plus c. So we have x plus 1 equals ax squared plus a plus bx squared plus cx. And then we want to group like terms together. So I have a x squared plus bx squared. At the end of the day, I can factor out an x squared from both of those and have a plus bx squared. And then I have plus cx and then plus a. On the left-hand side, I don't exactly have an x squared term, right? But I could cheat and use a placeholder as 0x squared. In other words, a plus b, the coefficient of x squared over here, must equal 0. And then the coefficient of x, c, must be 1. And then a must also be 1. Then I need a value for b, so plug a into this formula. 1 plus b is 0, so b must be equal to -1. Okay, so I can rewrite my integral as 1 all over x plus -x bx plus 1. I'm going to rewrite that as 1 minus x all over x squared plus 1. Okay, the first guy is a natural log. This guy is a mix, right? There's kind of this inverse tangent guy there, and then a bit of a natural log there. Okay, so let's integrate the first part, ln absolute value of x. You have to remember to evaluate that, plus the integral of dx all over x squared plus 1, and then minus the integral of x all over x squared plus 1 dx. So this guy, ln absolute value of x, is as is. This guy is an inverse tan, right? It's just straight up tan inverse. It's 1 over a, but a is 1. U is x, so there's really nothing to do. Tan inverse of x. And then this guy requires a u sub, right? So u for x squared plus 1. Du is 2x dx. So dx is du all over 2x. So it's going to result in a constant of 1/2 being pulled out. And so we have minus 1/2, and I have to remind myself to integrate this, evaluate this, minus 1/2 times x all over u times du all over x. Okay. Moving on. This will equal then ln absolute value of x plus tan inverse of x minus 1/2 times the integral of du over u, which of course is a natural log integral, so we're ending ln absolute value of x plus tan inverse x minus 1/2 ln absolute value of u. U, though, is x squared plus 1 from above. And then we evaluate from 1 to 2. So moving on, this is equal to ln of 2 plus tan inverse of 2, I'll need a calculator, minus 1/2 ln of 5 minus ln of 1 is 0, tan inverse of 1 is pi over 4, and then minus 1/2 ln of 2. Cleaning up just a little bit so I don't have so much work in my calculator. Ln of 2 minus negative 1/2 ln of 2 is going to give me 3/2 ln 2, and then plus tan inverse of 2 minus 1/2 ln 5. I guess there wasn't very much to do there. Minus pi over 4. Plopping that into my calculator, I don't know what I got. Yeah. I don't know. The book is going to try to combine these two natural logs. There's no big deal. You can use power rules. So this would be ln of 2 to the 3/2 plus tan inverse of 2 minus, or rather plus, ln of 5 to the negative 1/2 minus pi over 4. This would be ln of 2 cubed is 8, and then we want the square root of 8. So you would get square root of 8, and then this thing is 1 over square root 5, so over square root 5. Then plus tan inverse of 2 minus pi over 4. And then finally, I think they pulled out the 1/2 power from this, because you could rewrite this as ln of 8/5 to the 1/2 plus tan inverse of 2 minus pi over 4. And then they brought up the 1/2. Okay, so, you know, obviously this answer way back here is fine. You probably want to just give me a decimal approximation. But when you look in the book, they're going to give you probably something like this. And all they're doing is condensing this answer as much as possible to fit more in the book. You know, they're saving money on paper and on ink. You want to look in the back of the book when you're doing your homework. Make sure your answers kind of look like their answers. That's going to make your answers on the test look more like you've been doing your homework, right? So, I mean, that's kind of one of the things I'm doing when I grade your test. I'm just looking to see if you're doing your homework, you know. Okay, so yeah, somebody just asked me the other day, how much should I simplify? And I kind of told them, you know, if you've been doing your homework, checking your answer in the back of the book and trying to make your answer look like their answer, that's good. Okay. All right. So thanks for watching. Bye.